Introduction. Aircraft pitch control is a fundamental aspect of aviation engineering that focuses on managing the aircraft pitch angle to ensure stability, maneuverability, and safety during flight. This involves the use of mathematical models, feedback control strategies, and simulation tools to analyze and optimize the system behaviors under various conditions. By leveraging advanced techniques such as root locus, time response, and frequency response analysis, engineers can design controllers such as PID, PD, and fuzzy logic controllers that enhance system responsiveness and stability. These methods are vital for addressing challenges like external disturbance and nonlinear dynamic, ultimately contributing to safer and more efficient flight operation. Problem setup. This is the problem that we receive from the aircraft pitch system modeling. The primary challenge lies in ensuring the aircraft maintains a desired pitch angle for stable and efficient flight while compensating for disturbance such as wind gusts, turbulence, or changes in thrust and weight. Improper pitch control can disrupt the balance between lift and weight or thrust and drag, causing the aircraft to deviate from its intended trajectory. This system would take real-time data from sensor monitoring the aircraft pitch and compare it to the desired pitch angle. The controller would then adjust the control surface to correct any deviation. Advanced technique like root locus and frequency response analysis can be used to tone the controller parameters for optimal performance, ensuring stabilities, quick response, and resistance to turbulence. Objective. The first objective of our project is to develop an advanced control system for managing the pitch dynamic of an aircraft, focusing on enhancing stability and responsiveness during flight. The second one is to validate the effectiveness of the proposed control system through simulation and testing. The third one was to overcome the limitation of conventional PID controller, which often rely on fixed gains that may not perform well under changing conditions, such as wind disturbance or variation in aircraft dynamic.
And next are the literature review. What we get for aircraft pitch, research has made significant strides in the control and analysis of the aircraft pitch dynamics as an essential aspect of aviation stability and performance. The study titled Aircraft Pitch Angle Control Using Feedback PD and a First Order Compare Center by Gala Ali Hassan and Mustafa Gamal Abdul Majid developed into the various control strategies, including the feedback, proportional, the derivative PD controller, and the first order compensator. This research methodology compares these strategies to traditional proportional integral derivative ataupun we call PID controllers, highlighting the depth efficiency enhancing step that a first order compensator in the particular offer compelling alternative to the conventional method due to the capacity to the streamline and the control process and reduce the system complexity. Aircraft pitch system. In the quest to improve the control of stability of aircraft, research study have the focus extensively on the analysis and modeling of pitch control system. A key contribution from Hassan et al. is to investigate the use of PD and a first order compensator to manage aircraft pitch angles. They study to compare this compensator with a traditional PID controller and demonstrate that the proposed compensator enhance step-time response and overall system performance, suggesting critical advancement for the flight control system.
Hi, my name is Ahmad Alami Effendi from my part Chapter 3, Root Locus, Time and Frequency Response Analysis. Firstly, root locus analysis of the aircraft pitch in the MATLAB. Root locus analysis is used to design stable control system for aircraft pitch. By plotting the root locus in the MATLAB, with RLocus engineering can visualize how the system pole move as a control gain change. This helps in stabilizing the pitch angle by ensuring pole shift from instability right half plane to the stability left half plane. Next, time response analysis of the aircraft pitch in the MATLAB. Time response analysis evaluate how the aircraft pitch react to the disturbance of the control input over time using MATLAB tools like Simulink, engineering analysis, metric, such as rise time, settling time, and overshoot through the step response plot. This ensures the control system stabilizes quickly and minimize overshoot, enhance flight efficiency and safety. And lastly, frequency response analysis for the aircraft pitch in the MATLAB. Frequency response analysis assesses robustness against the disputes like a wing gas MATLAB tool, like body plot and quiz diagram analyze stability, margin, and the resonance frequencies. This insight ensure the control system maintain stability and reject periodic distributions, ensuring reliable flight in a challenging condition. That's it. Okay, for the analysis of the root locus with a simple proportional control aircraft pitch, as the graph show, the root locus plot that show the how closed loop pole shift as proportional gain k increase. Starting from the open loop pole at the origin, the pole move along the real axis into the complex plane, often leading a instability as they enter the right half of the S-plane. This highlight the limitation of the proportional control for stabilizing aircraft pitch. To achieve the greater performance, advanced strategies like PID control or lag compensation are needed. Root locus analysis provide key insight for the designing effective control system. Root locus analysis for aircraft pitch dynamic. A pre-compensation block Fs is equal to 0.2 scale the unit step input to the desired reference of the 0.2 radians without altering the root locus plot. Design requirements such as a settling time, percent overshoot, and rise time based on the natural frequency are added as a guideline on the root locus plot for the flow placement. Although the aircraft pitch system may not perfectly match a second order model, this criteria provide a solid starting point. The design process involves creating compensator as such lag or PID to shape a root locus, placing closed loop pole in the desired region, the iteratively simulating the refining system to ensure performance goals are met. Next, effect of the lead compensator pole of the closed loop pole location. As a graph, adjusting the lead compensator pole location shift the root locus branch, align them close to the desired performance region. While 3 branches pass through the target region, 1 branch on the real axis remain outside. A closed loop 0 at the negative 0.1541 reduce the impact of this lower pole. As loop gain k increase, this pole move closer to 0, minimizing its effect on the transient response. The current closed loop pole location marked by a pink box inside the leftmost pole has negligible influence due to each much faster than me. For open loop system response of the aircraft pitch dynamic. The open loop step response of the aircraft pitch dynamic show unstable behavior, with the pitch angle increasing without the bound and no steady state value. This instability highlight the need for controller to stabilize system and achieve the performance objective. Overshoot is less than 10%, rise time less than 2 seconds, setting time less than 10 seconds, and steady state error less than 2%. Designing a stable controller is essential to meet these criteria and ensure stable desired performance.
Hello. Okay, so for PID control, there are three. First one is P, represented as proportional controller. Second is proportional integral, which is PI, and the third one is PID, which is proportional integral derivative. So for the proportional ones, the controller adjusts the elevator deflection proportional to the pitch error, which is difference between the desired and actual pitch angle. Then the proportional gain, which is Kp, determines the magnitude of the correction. And then the second one is this Pi. It is integral terms to the proportional control. The integral gain, which is Ki, accumulate past errors over time, helping eliminate the steady state error. And then the third one, which is PID, which is a combination of P and Pi, the derivative and the proportional ones. In terms of the terms, so the represents as KD, It predicts the future error based on the rate of error change, helping the oscillation and improve stability. Hello. So for the next one is the comparison of three of them. So based on the graph, for the P, it reduces with proportional. It reduces the steady state error but cannot eliminate it completely. A higher KP improves responsive but may introduce oscillation or instability, primarily influence system rise time and overshoot without addressing persistent errors. So for the application, it's suitable for initial correction of pitch but limited in achieving precise stabilization. So we move on to the PI, which is on the left side. It eliminates steady state error, ensuring better pitch stabilization, slower response compared to P control due to integral terms. If Ki is too high, it can introduce oscillation and reduce stability. So for the final one is PID. It provided the fastest response and minimal overshoot by dampening oscillation, eliminates steady-state errors while maintaining stabilities, offers superior control by balancing rise time, overshoot, and settling time. That's all from me. Thank you.
Conclusion. This study analyzed aircraft pitch control dynamics, highlighting the critical role of feedback controllers in ensuring stabilities and safety. Using methods like root locus, time response, and frequency response analysis, it demonstrates the superiority of PID controller in achieving quick response times, minimal overshoot, and steady state error elimination. MATLAB simulation validates this finding, showing enhanced stability, margins, and compliance with performance criteria. The research underscores the value of integrating theoretical and computational techniques to develop robust control solutions, contributing to advancement in aerospace engineering and improved handling of external disturbance.